Hello, everyone. Welcome, welcome, welcome to the free GRE Prep Hour. All right. We're going to be using the chat window to say hello here. So just try typing in the chat, say hello if you can hear me, and let me know where you're dialing in from. Got some folks in LA, Scranton, Michigan, some more LA. Well, I'm dialing in from the Manhattan Prep offices in beautiful Manhattan. Hope you guys are all doing well on this lovely evening, and I'm excited to have you here. We've got a lot of really exciting content to cover. So here is how this is going to work. Hopefully you all can see this PowerPoint here. We are doing a free GRE Prep Hour. We offer these every 2 weeks to give you guys a chance to learn some GRE content that you wouldn't necessarily get out of a book. These are extra expert tips that you can't find anywhere else. So let's get started. Before we begin, just want to say that the problems that we do here in class are problems written by Manhattan Prep instructors. If you want more of this great content, check out the 5-pound book of GRE Practice Problems. This has more content, more GRE content than you might ever even need. Tons of problems, great advice in there. So we are going to get started. Here's what we have on our plan for tonight. We're going to be doing quantitative comparisons. So just tell me in the chat, how many of you, how about this, how many of you have taken the real GRE before? Do we have any GRE experts in here? A few of you have taken it Saturday, congratulations, or should I say good luck. Have any of you taken a practice exam? All right, a lot of people here have taken practice exams, great. If you haven't, that really should be the first thing that you do to start your prep is dive in, take a diagnostic, see how it goes. If it doesn't go well, that's all right. That'll just tell you what you need to learn. So, quantitative comparisons. We're going to be looking at some patterns in quantitative comparisons. But actually, before we get into that, let's talk about what quantitative comparisons actually are. Can someone give me just a quick rundown, if you had to explain QC, as we'll call it, to someone who's never seen it before? What is QC all about? I like that. Which side is greater? So you'll have quantity A, you'll have quantity B, and what your job is, oh, giant U there, is to determine which one's greater. So if they gave you a nice easy one like 2 versus 4, oh, wouldn't it be nice if they were all that easy? But that's the basic idea. They give you 2 quantities that you may or may not be able to compare. And the answer choices are always going to be the same. Answer choice A would stand for quantity A is greater. And then I bet you can extrapolate from there what B might stand for. B would mean quantity B is always greater. C means the 2 are equal. And D means cannot be determined. So if you've never studied for the GRE before. This is something that you're going to want to get used to because this is a question type that doesn't exist anywhere except the GRE. And it's something that if you get really good at practicing it, it can be a time saver. You can move through these really quickly and you can gain a lot of points here. One thing that I like about QC as opposed to other problem types is, well, there are only 4 answer choices here as opposed to 5 answer choices on standard multiple choice and things like that. So let us do this. You know what? I'm just going to throw you guys into the deep end. I'm going to give you a set of problems to work on, and then we're going to figure out what the patterns are, what the theme is. So what I'd like you to do is just keep track on your own paper. Don't type in the chat, please, but keep track on your own of what answers you get for these, and then we'll talk about what patterns we can discern. So, oops, I'm going to go back for a second. Forgot that I had to erase. We're working with a new format here. This is called Zoom, which has lots of cool video functions and things like that. But I need to remember that I have to erase everything I have on the screen before I move on to the next. So give me just one moment here. We will erase all of these marks and give this set of problems a try. What I'll do is I'll give you 6 minutes on your own to work on this set of 3 problems, and then we'll discuss. All right, go for it. 1 more minute. All right, let's discuss these. Now, we'll come back to these in just a moment, but I want to talk about the idea of patterns, for just a second. Quantitative comparison patterns. Sorry, this light's a little aggressive. There we go. How about this? Tell us in the chat. Don't tell us what answer you got, but did any of you guys find that you were getting the same answer for all of these? There's definitely a pattern at play here. Or the same answer for some of them. No, got different answers. Don't tell us what you got, but just tell us if you got same answers or... All right. So I want us to see if we can detect what pattern was going on here, and it really has to do with this. If I can impart my one favorite bit of wisdom about the entire GRE, it's be skeptical. If it seems like they're trying to direct you toward a certain answer, ask yourself, is something going on here? Maybe it's not as easy as it seems. And so the pattern that I want us to talk about here is what I like to call the easy C. And so the idea here is beware of the easy C. So what do I mean by that? Well, let's take a look. This first one, yep, that text stays right there on the screen. I'm going to remember that one of these days. This one definitely feels like these two quantities, quantity A, quantity B, they're kind of giving us the same sort of idea, right? Oops, didn't mean to click that forward. These look like they are quite similar. So it seems pretty reasonable that if they're structured the same way, they seem to be leading us to the same thing, that the answer would have to be C, right? Two quantities are equal. But when you feel like they're leading you too strongly towards C, I want you to push back and I want you to be careful. We're given that K is a prime number. All right. So let's just start by defining this. What is a prime number? Someone give me the definition. Yeah, a prime number has only two factors. It's only divisible by 1 and itself. So that's what we need to know about primes. So K is some number divisible only by 1 in itself. And one strategy that we use a lot on GRE, on QC, is testing numbers. So you might have tried testing. Let's try 2. K is 2. So if we use 2 for K, then 7K would be 14. All right. Well, what are the distinct factors of 14. And here's where I want us to really pay attention to terminology. Number of distinct factors. That's definitely going to matter. Distinct factor is anything that divides into a number. And distinct, well, means not repeating, can't repeat numbers, exactly. So we don't want to just think about prime factors. Some problems ask us to do that. Here we want to think about all of the distinct factors. So to get 14, it could be 1 times 14, or it could be 2 times 7, right? So in total here, we've got 4 distinct factors. And then if we try the same for 11k, so 11k equals, well, if k is 2, 11k is 22. And so then the distinct factors of 22, we've got 1 times the number itself. We've got 2 times 11. All right, well, then once again, we've got 4 distinct factors. So it definitely seems like we're going to get a pattern. We're going to have 1 times the number itself. Oops. We're going to have k, and we're going to have times 11 over here, and then k times 7 over here. So seems like they're going to be the same. We could test another set of numbers. We could test 3. So where k equals 3, then we've got 21. So 1 times 21, 3 times 7. All right. And then over here, 11k would be 33. So 1 times 33, 3 times 11. We're getting the same thing every time, right? So usually on the GRE, if you test a couple sets of numbers and you're getting the same result, you know, maybe you could pick that. But here's what I want you guys to think about. When you're thinking about testing numbers and whether you should test more numbers, this is the rule that you should use. Always test at least 2 cases. But then that doesn't necessarily mean that you're done when you test 2 cases. Then think, is there a way to get a different result? Let me scoot those up. So I want us to think here. Right now we're getting 4 distinct factors every single time. I want you guys to think about, in particular, the terminology that they gave us, and ask yourself, is there something that we could test that would give us a different number of distinct factors? And maybe the key is to think, what wouldn't be distinct? Anna nailed it. Test 7 or test 11. Think about, why did they use these numbers here? What's special about those? Sneaky, right? So sneaky, and you can count on the GRE to be sneaky. So if we test k is 7, then over here, well, normally we would have 1 times 7 times 7, 49, and then 7 times that number. But because we're only looking for the distinct ones, we don't want to double count. So here we only get 3 distinct factors, whereas with 11, 7 times 11, we're still going to get 1 times 77 and 7 times 11. So 4 distinct factors. So if there are cases where sometimes we have 3 in A and 4 in B, or sometimes we have 4 in A and 3 in B, then the answer must be D. Oof, brutal, huh? This question I found, this is a question that I wrote thinking that it would be like medium to hard, and this question stumps almost everyone. This is universally considered one of the hardest problems, probably the hardest problem I ever wrote. Didn't even mean for it to be that hard, But I know, right? So unfair. I can tell you from personal experience, when I write these questions, I'm messing with you in exactly the same way that the test writer on the real test is messing with you. They're not, being unfair. They're not giving you rules that don't exist or making you do tons and tons of really difficult math, but it's making sure that you're answering the right question. Are you really answering? Yeah, you guys know Ethel from our classes. We'd like to think about the test writer who's sitting behind the scenes going, how can I mess with people's heads? So I want you guys to push back against the obvious. That's always the goal. So I'm going to clear all of these drawings and have us move on to the next one. So what I want you to do is this. Take another moment to think through this one. If you found that you got C the first time, I'm just going to go ahead and tell you the answer is not C. See if you can think about what it is. Don't type it in the chat yet. Let everybody take a moment to try to think about it, but then we'll discuss. Okay, let's take a look at this. Yeah, I agree that this one is tricky as well because it really, really feels like the answer should be C. If we've got something squared and that's equal to, oops, I keep clicking on it and then it moves to the next screen. If something squared equals something times something, if x squared is equal to x times another thing, well, x times x equals x squared, right? So I'm looking at this and I'm thinking, it has to be the case that x equals y, right? That's the thing that makes intuitive sense here. So x squared, look, we can even prove this algebraically. X squared equals x times y. So, I mean, it makes intuitive sense that x equals y, but let's prove it. Let's divide both sides by x. Divide both sides by x. Okay, so like that cancels, one of these cancels, and we end up with x equals y, right? And if x equals y, then the absolute value of x must equal the absolute value of y. Okay, if any of you guys are thinking like, wait, okay, yes, I'm with you so far, but you said it wasn't C, it means that there's something that we forgot to consider. Anna's crushing it tonight, yes. This right here, we're only allowed to do that if x is not 0. You're only allowed to divide by a variable if it's not 0. Why is that the case? What's the deal with 0 when we divide? Why is that a rule? Well, if we imagine, I mean, you could start with nothing and divide it into parts, it would just be parts of nothing. But can you take, like, imagine taking like 10 apples and dividing them into no parts? Doesn't make any sense. So dividing by 0 is undefined. So you're only allowed to divide by a variable if you know that it's not equal to 0. So think about it. In this case, if x squared equals x times y, what happens if x is 0? Precisely. Y could be anything. We don't know the value of y. And as such, there's no way that we can compare x and y. So once again, the answer has to be D. Ooh, sneaky. It often turns out to be the case. I'm not going to say always, definitely not always, but it often ends up being the case that if they seem to be steering you really strongly towards C, the answer might end up being D. There might be some other variable, some component about this problem that we just don't know enough about. Right, exactly. So how about this? If I gave you this additional piece of information, if I said x squared equals x times y, and how about this? Product xy is not equal to 0. If they told us that the product couldn't be 0, then neither one of these could be 0, and then they have to be the same. Then we would be allowed to divide by x. But if x could be 0, then, so let's test cases here. Let's, for example, going through and testing cases, because I have some questions on this and I agree that it's tricky and I want to make sure that we clarify. So basically, case number 1 is where x equals 0 and y equals 5, right? So in that case, quantity A is 0, quantity B is 5, and so quantity B is greater. And when we think about our QC answer choices, A, B, C, D, well, that means if we found a case where quantity B was greater, it's definitely not going to be A, it's definitely not going to be C. But then we could try a case where x isn't 0, where, for example, let's say, how about this? How about x and y are both negative? X is negative 2, and so then negative 2 squared is 4, so to get that, it would have to be y equals negative 2 as well. And then the square root of x would be 2, square root of y would be 2, and in that case, they would be equal. Well, if we found a case where they're equal, the answer can't be B, quantity, because B would have to mean that quantity B is always greater, and that's where we would pick D. Sure, yeah. Omer, to your question about, well, why not just square root both sides and then we get square root of x times y, I think we'd run into the same problem there. Like, I'm not sure how you would use that to compare absolute value of x to absolute value of y, because the square root of xy could be, well, we'd be like, okay, well, x versus the square root of xy, we just wouldn't know how to compare those. So I'd say that that's one of those cases, like if we, over here, square rooted that to say x equals the square root of product xy, I don't think that this gives us any extra information. If product xy equaled 81, then x and y would both be 9 or negative 9. In this case, the thing that we know is that if x is not 0, x and y will be equal. But since x can be 0 and y can be a non-zero, there are cases in which they wouldn't be equal. So that's the idea. That's what gets us to the answer D, because we didn't have this constraint here. Yeah, but this stuff is tough, and it's tough not because it's difficult math content, right? It's tough because the GRE is messing with our heads, right? They know that we forget about negatives, we forget about 0, we forget to test fractions and things like that. And they will play with your assumptions. They will use your own weakness against you. One really cheesy trick that I always use is I say, okay, Think of a number, any number, and I'm going to try to read your mind. All right, go ahead. You guys can all think of a number, any number. I'm going to see if I can read your mind. I bet, well, maybe not after doing this exercise, but before this, if we'd done this, I bet you guys would all have been thinking of a positive integer, right? If I say think of a number, any number, we automatically go to like 1749, right? Nobody ever says negative 3.2. So your assumptions when you hear words like number and things like that are what they use against you. So let's talk about how to turn our weaknesses into strengths. Here's what I want you guys to do with something like this. I want you to make flashcards. So here's how you make good GRE flashcards for quant. Well, I mean, you can do these all on paper, on the single sheet of paper, but I really like individual index cards that you can flip through like this. And then you would, on one side, just write this little piece of code. And then on the back, you would write the translation of that code. So how would we put this into a nice succinct format? Next time we see something like this, how would we want to translate it? I would say it like this. I would say x equals y if x isn't 0, or if x is 0, y could be anything. And then put down the cases you tested. Put down additional reminders. I didn't give myself very much room on this. So you might want to put a reminder in a different colored pen. Reminder, can't divide by 0, things like that. Yeah, because a lot of times with GRE Quant, it's not just about the rules. You might remember that rule that you can't divide by 0, but it's recognizing when and how they apply it. And so I think that these kinds of flashcards can be really helpful. Let's do this. I think that we could practice some more of this because I think that this is such an important concept. Let's make a few more of these flashcards for quant translation. I want you to try each of these on your own. Is it going to let me draw here? Oh, it's because I'm trying to draw in white. Let's try some coded language and think about how we would decode it. So I'll write in a font that is small enough to actually see. Let's say that one. It's another one. All right, take just a moment to try to decode those on your own. had to go get a portable fan. The AC, whew, it's broken in here. It's warm in here. Hope you guys are all staying cool wherever you are. All right, so let's talk about how we would translate each of these. What is the code that's really being tested here? So here's another one that, well, maybe looks a little weird. The absolute value of n equals minus n. But I thought absolute values always had to be positive, right? So how could it be equal to a minus? How are they trying to mess with our heads? What's really going on here? Aha! What if n itself is negative? Then putting a minus in front of a negative would make it positive. So n is negative. Is that the only possibility? Ooh, I like that way of saying it. Non-positive. N is negative or 0. Or in other words, it's non-positive. The GRE doesn't say non-positive very much, but if you ever see them say non-negative, remember that that doesn't mean just positive. Non-negative is 0 or positive. All right, cool. K equals 2p plus 1, where p is an integer. I mean, at first glance, you're like, okay, so what? This is just some random information about some variables, k and p. But there is something very specific that this is telling us. If p is an integer, then 2p, 2 times any integer, is going to be even. And then an even plus an odd, plus 1, plus any odd, but particularly plus 1, it's got to be odd. So k must be odd. What about p? Is p odd or even? Oops. What did I just do? Oh no. Okay, there we go. P doesn't matter. Yeah, k is odd, p could be even or odd, we don't care, it doesn't matter. This, like, basically, the GRE could just come straight out and tell us, hey, k is odd, and then we'd have a lot of information, but they don't want to be that nice to us. They don't want to give us the information straight up. They want us to unpack it. So k is even because anytime you have an even time, I keep doing that. Why do I keep doing that? Anytime you have an even times an even, it's going to be, an even times anything is even. So even times anything equals even. So when we had 2, 2 times p had to be even. Again, keep doing that. Alrighty. Let's look at this last one. The remainder when x is divided by 10 is 3. What do we do with that? Well, maybe we just think, well, but if we divided 30 by 10, we'd get 3 as the quotient, but not the remainder. Remember, and for those of you who learn division in the US where we do it like this, if we take 23, for example, and we divide it by 10, 10 goes into 20 2 times, and then we go, okay, 2 times 10 is 20. Okay, that gives us a 3. 10 doesn't go into 3, so we have a remainder 3. In other countries and other systems, the setup is different, but the process, the idea is the same. Oh wait, can you see it now? Hopefully. Sometimes it might take a second to show up. This is a new format. It's the same as before. You didn't see me writing anything? Oh, you can see it. Okay, good. I was just writing it outside the box, not inside the box. So the idea there is that the remainder, that's what's left over after dividing. So two key things that we know: whenever we divide something and we get a remainder, that means it's not evenly divisible. So we could actually start by saying x is not divisible by 10. That's something we know. But what else do we know? There's something special about the dividing it by 10. That's going to be a little bit different. I mean, if we said remainder when we divide by 6 is 3, remainder when we divide by 11 is 3, would give us different information. There's something special about dividing by 10. Think about when decimals move. Dividing by 10, multiplying by 10 is all about shifting the decimal point, right? So if we divide by 10, we've effectively shifted the decimal point. If we're left with 3, that means the units digit of x is 3. The only numbers that are going to give you a 3 as a remainder when you divide by 10 are numbers that end in 3. 23, 33, 43, 53, or it could be a number in the trillions as long as it ends in a 3. Cool. So I highly recommend practicing. Yep, absolutely. I can explain the first one again. So the idea here is that if the absolute value of n is equal to minus n, well, we'd want to think with absolute value, there are 3 relevant cases. There are negatives, there are positives, and then there's 0. If we tested a positive, imagine testing 2. The absolute value of 2 equals negative 2. Nope, that definitely doesn't work. But if we try the absolute value of negative 2 and ask if that's equal to minus negative 2, yeah, that'll work. And then 0 works because it doesn't matter whether we put a minus in front of the 0 or not. Absolute value of 0 equals 0. There's no such thing as plus or minus 0. Did that answer your question? Yep, the idea with units digits is if and only if we're dividing by 10. This is the code here. When we divide by 10, divide any number by 10, the remainder that you get is the units digit. So that's not true of any remainders. If we're dividing by anything else, that's not going to be the case. Specifically, this code is about 10. Adam 45, did that answer your question? Excellent. All right, so let's look at the next one that we did. I've got a bonus question for you guys. Given that my name is Céilidh and it's spelled with all kinds of silent letters and everything, I thought I'd give you a question with some traditional Irish spellings in here. So does anyone know how to pronounce this first name? Any guesses? This is why I love traditional Irish spellings. This one is pronounced Aoife. Second one, it's pronounced Cuiva. And the third one, maybe some of you have seen that before. Does anyone know how to pronounce that one? No, it's pronounced Neve, or sometimes Niev. So just learn something that has nothing to do with the GRE, just for fun here. So here again, it sort of feels like the test writer is leaning us toward C, right? Like one was 15 up, 15 down, the other one was 30 up, 30 down, so should balance out as totally the same, right? Plus 15 minus 15, plus 30 minus 30 just gets us back to where we started. All three of them are the same. I think a good rule with that idea of be skeptical is if there's a hunch or an answer that you got to when you're like, I bet it's that. That feels good enough. It's really not going to be that simple, right? So there's something else going on here. Here we actually have to dig in, do the math, test the numbers. So you could do this purely algebraically. You could test values. It really doesn't matter. I think testing values keeps things nice and simple. So let's start with Aoife. Let's say that Aoife has a nice square garden, keep things really simple, and this garden is, well, if we're dealing with percents, let's just test 100 and 100. That makes life the easiest possible. So then, if we're testing that, then Quiva's garden, what are the dimensions? The length is 15% greater, so 115. Width is 15% less, so 85. All right. And then we've got Nieves. So here, 30% greater and 30% less, we're looking at 130 and 70. Well, there, all we have to do is plug those into a calculator. Oof, thank goodness the GRE gives you a calculator. It makes life so nice, right? So I'm going to pull up my own calculator because I don't know 85 times 115 off the top of my head, nor should anyone. That would be crazy, right? Uh-oh. My calculator disappeared from my screen. I'll make you guys do the hard work for me. We plug 85 times 115 into the calculator. All right, we got 9,775. All right, 130 times 170, what do we get? 9,100. Okay, so remember I said before that if you're testing values, you should always test two sets of values, right? So we could try another set and see if we get different results in a different case. But let's think about this. When we're testing different values, one good rule is think about extremes, go really big or go really small. So you could do order of magnitude, and you could think, well, what if we shrink this down to 1 by 1 instead of 100 by 100? And then that would make this 0.85 and 1.15, 0.7 and 1.3. But that actually wouldn't change the comparison between them, right? Or we could think about this algebraically. How many of you guys set this up algebraically? Yeah. So we could say, you know, we've got some length, some width. Pick variables for those. L and W are usually good ones to use. And then we're looking at 1.15 L times 0.85 W over here, and then 1.3 L times 0.7 W over here. And then what we get, the LW part is going to be the same. So we're going to get 0.9775 LW versus 0.91 LW. And as long as we're positive, right, which geometry, the gardens, you can't have negative gardens, right, has to be positive. So in that case, we can say, actually, you know what? This one has to be greater. So I don't want you to think that every time it seems like they're steering you towards C, the answer has to be D. That's not always the case. That was the case with a couple of the ones that we looked at. But there are certainly cases where superficially quantity A and quantity B seem to be the same, but in fact, if we do the math, one of them ends up being greater than the other. So the GRE, yeah, I mean, it's hard. You got to study for it, but it's not really about the math. The 15% greater than, 15% less, all this stuff about translating that into 1.15 and 0.85, that kind of stuff, you'll practice, you'll get good at that. It's making sure that you're answering the right questions and not falling for the easy assumptions. So my big recommendation to you, to avoid falling for those assumptions, what you want to do is, yep. To avoid falling for those assumptions, well, I mean, sometimes you fall for the assumption the first time. That's fine. There's nothing wrong with making mistakes. Mistakes are what you learn from. If you didn't make any mistakes, you wouldn't learn anything. But what I recommend doing is starting to track your work. So, to enhance your skepticism, I don't know how to erase that arrow there, but to avoid mistakes, to enhance skepticism, here's what you do. You track your work. Track your work obsessively. You want to keep, maybe in a spreadsheet, maybe just in a list somewhere, everything you got wrong and why you got it wrong. And then think about what you should change about your process. I mean, there will be some times that you're like, I just need to learn those geometry rules. That's fine. But a lot of times it's like, you know what? I need to put the pen down and really think about it first. I need to make sure that I'm considering negatives and zero and fractions and all of that stuff before I begin. There's great information in our blog about keeping an error log like this, keeping a review log, sometimes called. But what you want to do is, here's a really big one, spend more time reviewing than doing. A lot of us will just do problem after problem after problem and be like, got that one right, cool, got that one right, moving on, got that one wrong, what was the answer? Okay, moving on, what's the next one? I want you to obsessively review even the ones you got right. Some of you got some of these right, or a bunch of these right, or maybe all of them right, but I hope that digging into this and really thinking about the test writer was still useful even if you got them right. And then certainly if you got them wrong, you want to think about what you should change, what you should do differently. So more time reviewing than doing. Here's a good example. If a practice exam takes 2.5 hours, take 3 or more hours to review it in depth. And what that involves is redo all the problems. Think about different versions. Like write your own similar problems, kind of along the lines of when I was like, oh, what if it had said X can't be 0? What if it had said this? What if it had said that? Kind of play around with iterations and other versions and what that would do to change the problem. If there was something that you got wrong where the content's a little iffy, look for similar ones. And then read explanations to confirm. I mean, just like we did here, I gave you 2 minutes per question, which is even a little more than you should spend on test day, 2 minutes per question to do them. But we spent way more than that reviewing them, pulling them apart, really thinking about what the test writer was getting at and what we want to avoid. So that's what you want to replicate when you're studying on your own. Don't just do more and more problems. Make sure that you're really spending a lot of time unpacking, looking for your mistakes, and thinking about what needs to change. All right. So with that, if you want more GRE content, one thing that you can always do is try out a class. You can take the first class, first session of any in-person class or online class for free. You can also try Interact for 7 days for free. Interact is so cool. It's online, fully on demand. They're video lessons, and you get to do problems in the lessons. It suggests other things. It tracks your work. It is seriously such a cool platform. So check those out. If you're like, hey, I don't want to spend money on GRE Prep, I totally understand. There's a ton of free content on the Manhattan Prep website. Come to these free GRE Prep hours every other week. Read the blogs for content. There are other great workshops coming up. You can definitely do it on your own. It just takes diligence and it takes some thoughtfulness with review. Samantha, good question. I don't know those numbers off the top of my head. You can do the 1-month version or the 6-month version. Follow that URL. It's right on our website. In fact, I'll pull that up for you. Get that URL. 1 second. But yeah, it is a really cool product and definitely worth taking a look. If you guys have any other questions about what we have to offer or anything like that, obviously our website is a good resource. But you're totally free to email me. This is my I can't talk while I'm typing. That is my email address. If you have questions about prep options or anything like that, please do let me know. We're here to help you succeed. So I wish you guys all the very best. Thank you so much for coming, and good luck with all your studies. Take care.